Hello, everyone, and welcome back to Cyber Science. We now move into the track 18 of the conference. This track is titled Blockchain and Crypto, and we will have 3 different presentations between now and 7 p.m. So our first presenter is Johannes Mols from Aalborg University. I hope I pronounced the name right. Apologies if I didn't. He's presenting us a paper titled ethVote towards secure voting with distributed ledgers. So thanks for being with us today and for presenting your study to the conference. You will have approximately 20 minutes for presentation, so that we leave time for questions at the end. So over to you.
All right, thank you very much. Yeah, I'm Johannes Mols. I'm a student here at Aalborg University in Copenhagen. And this paper is focused about internet voting and its security aspects. And it is actually a semester project that I did. And we then decided to make a paper out of it together with my supervisor, which is also the co-author of this paper. Let me see if this works. Yes. So elections are obviously a very old topic. They have been around for a very long time, much longer than computers. And paper ballots are still the absolute dominant method of voting because they are proven to be quite secure, and it's very difficult to tamper with paper-based elections in a larger scale. And on the opposite, we have electronic voting machines and internet voting, which are much more vulnerable because they are able to be attacked through a large amount of different cyber attacks, and they scale much better. So if you find a vulnerability in an EVM or an internet voting system, you might destroy the entire election because it scales so well. So we thought, is it possible to design such a system anyway that is based on the internet, and can it be equally secure or even more? So the core contributions of this paper is a prototype titled ethVote, or ethVote for short. And we used the advancements in distributed ledgers and cryptography, and also present an entire list of requirements that are needed for a complete voting system to be considered secure. And we also provide a proof of concept implementation of the system that we propose. Our related work is, first we looked at Estonia's iVoting system, which is actually the first country to hold general elections over the internet. It is not based on blockchain, but more traditional internet systems. And independent security researchers have observed an election in 2013, and they identified serious vulnerabilities in both the technical aspects and the operability with the workers. So they urged them to shut down the system, but they are still actually running it. So then we looked at 3 further systems that are all based on the Ethereum blockchain. First off, we have BroncoVote, which is also a proof of concept using Ethereum smart contracts and homomorphic encryption. But it is a proof of concept, and there are many flaws that are not attributed for in this POC, such as an unsecured encryption, so a flawed registration process and further problems. Then there's a similar project called HAL. It is also a proof of concept with similar ideas such as homomorphic encryption, but in addition, it uses zero-knowledge proofs. It is also proof of concept, so therefore there are also some flaws in there. And lastly, we looked at Polis, which is a startup by the cybersecurity company Kaspersky, and they also built a voting system based on Ethereum. However, it is closed source, and they also use a private Ethereum blockchain, so it's really difficult as an outsider to verify any of their claims. Based on that, first, the requirements, they are actually taken from a paper that is solely concerned about the requirements for voting systems, because there are so many publications out there, and they looked at many of them and compiled a list that most of the papers share. So we took this list because it is a very good resource, and took this as all of them as the requirements for our project. We added a last requirement for the asymmetric key length that should be more than 2048 bits. But otherwise it is completely one-to-one from that paper. Now finally, our proof of concept. So it is also a system based on Ethereum smart contracts, and it both uses homomorphic encryption and zero knowledge proofs to verify votes. So first of all, smart contracts. Smart contracts are basically code that you can write and publish on the Ethereum blockchain, and it will run there, which is very useful to control transactions on the blockchain and specify certain rules, similar to Bitcoin, but it is more advanced and gives you much more options to actually control what is going on. So we used 3 of them. We have a registration authority contract, an election authority contract, and an election contract itself. The first one is solely responsible for maintaining a list of Ethereum addresses that are considered voters and can submit votes in actual elections. And we decided that the actual authentication of voters should be held offline because introducing an online authentication mechanism would just add a lot more vulnerabilities that we couldn't account for in this project, at least. And this will simply store the list of addresses that are registered offline. And then there's the election authority, which is maintaining a list of actual election contracts and is responsible for creating new ones and defining the restrictions of it, such as time limits, list of candidates, and so on. And then the actual heart of the system is the election contract itself, which accepts encrypted votes from voters and stores them on the blockchain. And it uses the smart contracts to check for certain restrictions, such as is the voter eligible, is the voter submitting a vote in the time limit of the election, is the vote valid, and so on. And the beauty of it is the homomorphic encryption, which means users can submit their vote in an encrypted form because it will be stored publicly on the blockchain, and we have to make sure that it is not anyone can just read what everyone voted for. So we used homomorphic encryption, which is a mechanism capable of performing operations over encrypted data. So a very simple example of it is multiplying 2 encrypted numbers, and this equals to the addition of the non-encrypted numbers, which you can then encrypt, which is the same result. So in essence, you can take 2 votes that are completely encrypted, multiply them in the encrypted form, and then you will get the sum of those votes. And then you can later take the private key and decrypt it to get the result without revealing who voted for what. Yes. And then in addition to that, how can we know that the encryption from voters and the decryption of the actual tally itself is true? How can we trust both voters and the election authority to actually be honest about this? And this is where zero knowledge proofs come in. So zero knowledge proofs allow you to prove a certain fact to a third party without without revealing the fact itself. So for example, if you encrypt your votes, you have to convince the election authority or the election contract that you only submitted 1 vote. So the vote only contains 1 vote, or as you could just vote 10 times for 1 candidate or for multiple candidates, which is not what we want. So this way, we can prove that the vote is correct without actually revealing what we voted for. And the same goes with the final decryption of the tally by the election authority. And then we created a proof of concept implementation, which is fully working unfortunately accept the zero knowledge proofs because it is currently very difficult with the current tools out there to create zero knowledge proofs that are complex in a way of encrypting and decrypting certain algorithms. Currently, we looked at one tool specifically, it's called Socrates, and you can add numbers and multiply numbers easily, but there's a very small limit to the actual number sizes that you can store, and it becomes very complex if you do more complex calculations such as encryption and decryption. Otherwise, the smart contracts are fully implemented, and we deployed them on an Ethereum test network. And in addition to that, we developed a front-end web application to interact with the contracts and actually make the system usable from a user perspective. And we hosted this web app on the interplanetary file system, in short IPFS, which is a decentralized network that naturally gives you some amount of protection against common attacks such as denial of service attacks. And the authentication of photos is done via MetaMask, which is a browser extension, and an Ethereum wallet. So this gives us the possibility of having a secure form of authenticating users without having to implement that ourselves. And then from the web app, users can actually interact with the contracts using a HTTP library that can directly communicate with Ethereum nodes. Then we also evaluated the prototype. On one hand, we did unit testing of the smart contracts to ensure there are no obvious mistakes while we were developing it, which was very helpful. And then we also externally verified the contracts after completing them with certain third-party services, and we didn't find any significant weaknesses or vulnerabilities, but of course there could always be something, so it's something to be aware of. And we found that all the requirements that we stated earlier were satisfied by one or multiple parts of the system. You can see a table on the right here of all the requirements that we have, and then the certain parts of the system that come together and fulfill these. But it assumes that the zero knowledge proofs are actually implemented. And then we also did an estimation of the costs of running such a system for an actual election. And it shows that it would be very expensive currently to actually conduct such a system for a general election currently. If you have 10 candidates in an election, one vote would cost you approximately $2 American currently, but this is fully determined by the Ethereum price. So if that goes down, your price of the election will also significantly go down. So how this can be improved is by either using private blockchains or reducing the key sizes, but that obviously comes also with their own significant disadvantages. Or another option could be Ethereum 2.0, which is not released yet, but could be a solution in the future to increase the performance of our system. So finally, what we presented in this paper is a proof of concept for internet voting using distributed ledgers, homomorphic encryption, and zero knowledge proofs. It has some limitations, such as the implementation that we weren't able to do of zero knowledge proofs and the aforementioned gas costs and limitations of the current Ethereum network. That could be a bottleneck. And in the future, we would like to add the implementation of zero knowledge proofs when that becomes possible or more feasible in the future, and also investigate the limitations that I just talked about. And that is it.
Thanks, thanks, Johan, for the presentation. For the attendees, please, if you have any questions, ask them using the Q&A feature that you see at the bottom of the screen. Just a quick question from my side there. Do you plan to try to have a similar approach or to test the proof of concept on other platforms for smart contracts other than Ethereum?
Currently not. I'm not aware of any other blockchains with similar advanced functionalities as Ethereum. I'm sure there are. But I found that the Ethereum platform is very friendly from a developer side because there are a lot of advanced functions that you need to actually implement systems such as verifying voters and storing them in a secure way.
Yeah, that's definitely the point of reference at the moment. So
yeah,
it makes sense to start from there at very least. So a question that's come through at the moment is what consensus algorithm did you use on your proof of concept?
Okay, it's the default proof of work concept from Ethereum. And what I mentioned with Ethereum 2.0 is the eventual switch to proof of stake, which would decrease the cost significantly and also make it more efficient, hopefully. That is what we're hoping for with Ethereum 2.0. So currently we're just using the default proof of work.
Why did you go for the default proof of work instead of trying other consensus mechanisms?
Because it was not so much about the actual blockchain itself. We kind of used it as a data storage, but other than that, we were not really concerned about the efficiency at the moment. So yes, in the future, we would definitely look at other blockchains.
Okay. There's a question from Martin. He's asking specifically which entities, persons, technologies, algorithm, etc. would a voter need to trust blindly in order to be certain that this vote is tallied correctly?
Okay, so in essence, no person, you don't have to trust any person if it is implemented correctly. The only person you will have contact with is the actual registration authority when you sign up for being a voter, which you will do in person with your passport or ID card. But after that, once your Ethereum address is in the system, you won't interact with any person. But then, of course, you will have to trust that Ethereum blockchain works as you expect, and the homomorphic encryption encrypts your votes as you expect, and the zero knowledge proofs also prove correctly that your vote is accurate, and you have to rely on the same algorithm that the final tally is also correct. So you don't have to actually trust the election authority to present you with the correct result, because the zero knowledge proofs will verify that.
Okay, and what benefits and challenges did you encounter in your implementation?
Okay, so the implementation was relatively difficult because it's such a new technology, and it is constantly being developed, and there are many updates all the time. So you always have to look out for any vulnerabilities or new features that come in. But otherwise, from such a technology, I would say it was comparatively relatively easy to implement such a system. And the only cons I can really think of is, of course, the gas costs, and that it's not very efficient. It takes approximately 10 to 20 seconds to actually register a vote, which is not scalable if you have multiple thousand or even more voters. Yeah.
Okay. And you mentioned earlier that there are e-vote online voting mechanisms which are not based on blockchain. Did you compare the functionalities and performance of your proof of concept against them?
We did look at the Estonian iVoting system, but after looking at that, we decided that we won't be going for any conventional internet-based systems, because the researchers there found that there are so many vulnerabilities that just come with the technologies that you use. So we didn't want to go for these technologies by principle, because by default, there are so many vulnerabilities that you simply can't account for in a system that is so important that there are zero vulnerabilities.
Okay, super. I think we have covered all the questions that we received. So thanks again for your presentation. We'll be back in 10 minutes for the next paper presentation, which is the second on this session. So thanks again, and
thank you.
10 minutes.